Thank you. So yeah, pushing the limits of materials testing, my AEngD is all about trying to find smaller defects, similar to the kind of ones that Maria was finding. So in the UK and all across the world, we rely very heavily on industry for keeping the lights on and transporting us to and from the places which we want to go. These industries rely very heavily on high-value manufacturing products, and the failure of any one of these products could result in something particularly embarrassing happening. This is completely unacceptable. This will cause the lights to go out, our planes to crash, and us not going to our holidays, essentially. So there's many reasons why this isn't a good thing to happen. It's expensive, it's embarrassing, it's dangerous, and also it's expensive. I said expensive because it's twice as expensive as it is embarrassing and or dangerous. There are things that we can do within industry, and I'm working with Rolls-Royce, and there are things that we can do in order to prevent this. One of them is to every so often overhaul everything, replace all the components so that we know that they're structurally sound. However, this is expensive. You're using more materials, you're removing components from, or removing entire engines, for example, from the service that it's normally providing, and therefore you're costing the company money. We could over-engineer all of the components, which we already do. However, this kind of builds in unnecessary length of time which it can be used, or unnecessary material, so this is also quite costly as well. However, if we're able to find defects before they can cause failure in these components, whilst the component can still be used within industry, then this is extremely useful, and this is essentially priceless. So, this is the area which we work in, and this is called non-destructive testing. Non-destructive testing is a huge array of tools that we can use. Some of them you'll come across in hospitals, so X-rays and ultrasound. We just steal those and we try and use them on components. There are other things as well, like dye-penetrant testing, and the area that I work in, which is electromagnetic induction of eddy currents. The basic principles, I'll run through it very quickly, is that you induce current in the surface of the material, and you couple that current to a primary coil, and any changes in the electrical properties of that coil tells you something about the condition of the material. And this is very sensitive, very simple. This is a very small coil that we use, and it's very repeatable as well. However, over the course of the past 50 years or so, as it's been used, the size of defects that it can detect has kind of plateaued towards this minimum of around 0.75, 0.5 millimeters in length, which is very small. It's one of the most sensitive techniques anyway. However, the introduction of complex geometries and of difficult materials means that the level of background noise in these materials is very high, which means that we might miss some of these defects. So if you've got a very large defect and you have a decision threshold where any signal that goes above it will mean that your component is rejected, then you're going to find it and it's going to be brilliant. You're not going to be flying in a faulty plane. If you have a smaller defect, which doesn't go above this decision threshold, then your component is still going to be accepted and continue to fly, and therefore could cause the failure later on because you haven't found these smaller defects. So my project is trying to find ways of pushing this signal above the decision threshold so that we actually find these defects earlier and so that components can go on for longer. Very simple analogy of the simple approach that we're using is if you have a mass on a spring and you oscillate it at a certain frequency, then it will resonate at a greater amplitude. This thing happens with coils as well, these coils that we were using to inspect. These are the equations, I don't want to go into them, but they resonate at a certain frequency. And we found that if you operate at a range of frequencies close to electrical resonance, so this is where electrical resonance occurs, and these three lines show you defect responses, or signal voltages from these eddy current inspections of three defects, then you get an enhancement region, which is outside what is commonly used within commercial probes and things like that. So we have this near electrical resonance signal enhancement, or NERSE, and it can push the defects signals above a decision threshold that you might set. So to show you this in a more visual way, I inspected a component at one of the common frequencies of 2.5 megahertz. These are all sub-millimeter defects, and you can find two of those defects relatively clearly above the background noise, but the other two you can't. Whereas if you operate at one of these frequencies within this band, then you see them all very clearly with a single shot. How this all kind of impacts, essentially it prevents us, well, allows us to find smaller defects sooner, so that it stops the planes from crashing on the road like that and continue to fly in the air. It also means that these high-value manufacturing components that we use these are kind of high-risk regions in red on this turbine blade there. It means that we can essentially make it a lot less likely to break in these controlled regions. And this saves money. The components can go on for a longer time. It also means that we can redesign them to save weight and essentially save money for the company and stop you from falling out the sky. So anyway, thank you very much.